Before starting my talk, let me say a few words. There is the war now, which brings a lot of blood and deaths now, and I strongly condemned the unmotivated Russian aggression and support the Ukrainian people. And I believe that sooner or later, the war criminals up to the highest level will be punished. And I'm sure that many scientists in Russia share this viewpoint. I could say it more, but it's not proper place. So let me start my talk. So I'll discuss the subject, which is, I hope, close to the mic interests, namely the random geometry and application of metric model to describe the random geometry. One part is devoted to analytic treatment of the problem, and it is the paper in preparation in collaboration with Vladimir Kazakov, Fedor Levkovich-Masluk, and Viktor Meshnikov. And the second part, which actually motivates the analytic story, is then concerns the numerical simulation in perturbed random regular graphs. There are several papers where different numerical simulations has been done. And also I'll turn to some application of this stuff to condensed matter issues. So the plan of my talk is as follows. First of all, I'll remind some well-known facts concerning the random regular graphs. Remind that random regular graph is the graph where degrees of all nodes are the same. When the number of nodes is large, the number of random regular graphs is large as well, and we can consider the ensemble of such graphs. Then I'll discuss the critical phenomena in random regular graphs perturbed by chemical potential. We introduce chemical potential for short cycles, and it turns out that there is non-trivial deformation of geometry imposed by chemical potential. Just numerical stuff. And then I turn to the analytic story, namely, I'll argue that there is new matrix model, which we have derived in collaboration with Kazakov, Levkovich, Masluk, and Meshnikov, which concern the quantum two-dimensional gravity coupled to massive spinless fermions. And then discuss the critical behavior in the corresponding model. The last part of my talk will be devoted to localization issues, ergodicity and fractality in perturbed and disordered random regular graph. Let me remind the well-known facts concerning the random regular graphs, how it can be described. The most simple way to describe this ensemble is to consider its spectrum. And it's possible to consider spectrum of adjacency matrix or Laplacian matrix, which are related in a very simple way. And consider the spectral density, the standard object in the random graphs or matrix models, and where the averaging over ensemble is assumed. It's known that when number of nodes is very large, then the spectral density in a random regular graph can be defined exactly, and it is so-called Thurston-McCoy distribution presented here. There are also a few points which I'll use later, namely that a multiplicity of zero modes of graph Laplacian is nothing but the number of disconnected subgraphs in the whole graph. The second point is that non-vanishing eigenvalue of Laplacian is proportional to the number of minimal number of cuts to get the disconnected subgraph, and its eigenvalue is known as the Fiedler vector. And final point is that when you consider traces of powers of adjacency matrix, or equivalently for random ergograph traces of Laplacian powers of Laplacian matrix, we just count the number of case cycles in the graphs. And this is well-known facts concerning the graphs, and the specific here is the Kirst-McCoy distribution for random regular graph. In the graph theory, it's very useful to consider so-called model of exponential random graphs. That is the sum of the graphs of some nature, and introduce and consider the partition function with different chemical potentials. So we consider chemical potentials for the different cycles. As I have mentioned, traces of powers of matrix denote the lengths of the cycles, and consider the partition function as a function of chemical potential. This is standard notion of exponential random graphs. And when you consider for instance, when the node degree is 3, it is just the random triangulation of the two-dimensional surface supplemented by some chemical potentials. From the viewpoint of statistical mechanics, here we consider ensemble, so-called mixed ensemble with fixed number of nodes, and however, consider the chemical potential for some cycles, for instance, 3 cycles and 4 cycles. What happens when we vary the chemical potential? It turns out that the graph undergoes the clusterization phase transition. It was found some time ago, and there exists the critical value of chemical potential for 3 cycles. When the chemical potential is larger than some critical value, there is a number of clusters. So the whole surface gets fragmented into a set of clusters, which weakly coupled clusters, and the number of clusters can be fixed. For instance, for random ergonomic graph, it is just the number of nodes divided by the degree of the node. So when you consider the random regular graph, the clusterized phase is just the one-step replica symmetry breaking situation. And when you consider more general distribution of degrees, then we have some distribution for cluster sizes. In what follows, I'll argue, and actually it was noted in the paper, that clusters can be interpreted as the eigenvalue instantons familiar in the matrix models. How the spectral density looks like. Before the phase transition, it is just the usual Wigner semicircle. And after phase transition, it acquires very peculiar form. There is the main band, which now it's not semicircle, it looks differently. And also some number of the isolated eigenvalues. And here is the graph for the adjacency matrix. And if you consider Laplacian matrix, eigenvalue instantor form the soft nodes. So clusters are just soft nodes in the spectrum of the perturbed graph. Very similarly, it's possible to consider random regular graphs perturbed not by the 3 cycles, but now by 4 cycles. And look what will happen. It turns out that the clusterization in this case occurs as well. And there is critical value of chemical potential for cycles. But there are now a few new features. The key feature is that now the clusters are bipartite, and moreover, it's not simply bipartite clusters, but it turns out that they are hypercubes. And it's a kind of surprise, but nevertheless, this is a result of numerical simulation, and it's known that such hypercubes can be considered as a kind of thermophile double state in several discrete modes. And once again, the number of bipartite clusters is fixed by the node degree in the RG ensemble. Here I present the pictures, how it looks like. In the upper picture, we have phase transition, first order phase transition for the number of 4 cycles when we change the number, change the chemical potential. Below, you see how the picture for the clusters looks like. And also I presented at the right picture how the adjacency matrix looks like. You see that there are bipartite structure, and all clusters are of the same size, and so we have a kind of one-step replica symmetry breaking phenomenon in this case. The phase transition can be analyzed all in terms of spectral density. It's the lower part of this picture. And the picture B, you see that below critical value, it is just a bit scaled Wigner semicircle. But above the phase transition, instead of Wigner semicircle, you have very different distribution. And also you have separated eigenvalues, which correspond to the number of clusters. So number of isolated eigenvalues correspond to the number of clusters. And this is actually a mathematical theorem from the graph theory. So you see that there is phase transition observed numerically, and in principle, it's highly desirable to get at least attempt to get the explanation of this phenomena when the two-dimensional surface get fragmentized in the clusters. To this aim, we suggested to consider matrix model, which look as follows. First, motivation. So, as I have mentioned, in the previous slides, I considered the chemical the potential in the graph ensemble is just the trace of Laplacian to the third power or to the fourth power. They are just chemical potential for 3 cycles and for 4 cycles. And instead, let us consider the potential which involves all powers. So not to distinguish short cycles, but consider the cycles of all lengths. This potential is just the logarithm of determinant of characteristic polynomial of Laplacian. And when we consider large M expansion of this potential, we just get the powers of Laplacians. So we could turn to previous potentials which provide the phase transition. So here is the here is the partition function of this model. Lambda is just can be considered as a cosmological counts the number of nodes. It is related to cosmological constant. Therefore, we consider parameter with two couplings, cosmological constant and mass. This model has at least three different interpretations. First of all, it can be considered that as a two-dimensional gravity, since we sum over all graph ensemble, but supplemented by massive spinless fermions. Just the integration over massive spinless fermions provide you a logarithm of determinant. So this is just result of integration of massive spinless fermions. On the other hand, it turns out that the same model can be interpreted very differently as a statistical model of weighted rooted trees in the forest, average of the random geometry. And finally, the third interpretation is it can be considered as a Hermitian one matrix model with non-trivial potential, which I'll derive in a moment. Let me remind for completeness the different matrix model for two-dimensional gravity coupled to one or another type of matter. Well-known pure two-dimensional gravity with a cubic potential. Then it has been generalized to the two-dimensional gravity coupled to d-2 matter and to the gravity coupled to Ising or Potts model. In that case, the multi-matrix model has to be considered. Later, there was a very important step where the MIC took important role, namely the double scaling limit has been invented. And finally, let me mention along the history story that the minimal strings and C=1 strings also can be considered. And for instance, for C=1, we have matrix quantum mechanics. The most close study, which to our work is the work first work with Caraccio, Jacobson, Salier, and Sakal. Actually, it's two-dimensional gravity interacting with massless spinless fermions, but supplemented by four fermion interaction at special coupling. It turns out that four fermion interaction simplify the problem, and in that case, the model is equivalent to the ensemble of unrooted trees in the forest. And let me say that we will consider the rooted trees in the forest, a bit surprisingly, without four fermion interaction, as the problem is more complicated. How we can derive the corresponding matrix model? We adopt two different ways. In this respect, by David and Kostov in Kostov MIPT paper, and the idea is to get anti-commuting coordinates. It is just the Parisi-Surlov trick, and in the context of matrix model, the Parisi-Surlov trick provides you dimensional reduction, and it was used for massless case by David. We have the massive situation, so we have a kind of generalization of this thing. And the proper generalization of Parisi-Surlov action in terms of superfield involves the mass in the following form. Then, using the conventional integration of anti-commutative variable, we could obtain the partition function in the following form. So you see that there is naively simple action potential in the exponent, but there is a non-trivial determinant. And it turns out that actually the essence of Paris rule of trick, we introduce a change of variables, which effectively cancels the determinant. And after all, we get the partition function of the matrix model, which looks as follows. We have Hermitian matrix X, and phi is solution to quadratic equation. In principle, this quadratic equation has two solutions, and it's necessary to select one. The proposition provides you the following potential for our matrix model. You see that there is some, it is a kind of non-trivial. So this is the standard Gaussian part. And the mass term is multiplied by this non-trivial function, lambda, let me remind, corresponds to cosmological constant. So this matrix model has two couplings, cosmological constant and mass. And in what follows, I'll try to provide you solution and our developments which have found at the moment. So how the shape of potential looks like? It's not difficult job to picture the potential. It has two minima, one extremum, one minimum and one maximum, and because of the square root, there is the wall. So there is some specific situation. So it resembles a bit the potential for the gravity, but shape is a bit different. Most complicated point is there is the wall due to a non-trivial form of the potential. There is another way to get the same potential in the matrix model. Now we use so this is the approach we have used to check ourselves. There exists the so-called matrix force theorem. I guess everybody from the university knows that there is called matrix theorem found by Golf, the determinant of Laplacian without zero modes is just the number of spanning trees in the graph. And it turns out that there is generalization of this theorem, which is very useful for us. The so-called matrix force theorem. First of all, it was found in mathematical literature by Chelnakov and Kelmans in '74, and then rediscovered in physics by David and Duplantier later. How it looks like? So the formula is simple and nice, and you see that the left-hand side will have characteristic polynomial for Laplacian of the graph, and we have the sum of different number of trees, and the parameter m squared just counts the number of L here is the number of trees in the forest. So we count different trees in the forest. There's factors here which where the product of different number of nodes in each tree, and the factor and the number of tree, and number of trees, and therefore the of trees in the forest, and this is important. Now, if let us use the same used this matrix for a theorem and use some result by Bondesson, Karachi, and Spartiella for a kind of brute force combinatorics for unrooted trees. So they used the theorem for derivation of potential for unrooted trees, and then it is different. The potential is different, and in our case, we use the result and use some trick. We could reproduce result derived by Parisian formulas. So we have two different ways to get the same function. Now we have potential, and as usual, the first step is the derivation of one cut solution. So one solution, but here we have new ingredients because of the square root in the potential. So there is a branch point C here, and one cut solution looks not too simple, but not too complicated. So it can express in terms of elliptic function, in terms of variables here are defined as follows. So C, A, and B are the positions of the branch point, and K here and E here are just elliptic modeling. So, so this is solution, and to get the proper asymptotics of the resolvent, it's necessary to consider the system of equation. And here I write down the system equation we have written, and it involves the elliptic modeling. The solution of this equation provides the critical curve. So instead of critical point, here we have critical curve, or the plane C remains related with the cosmological constant, and M square is the mass of the fermions. It turned out that this critical curve divides the plane into two pieces. Upper region of enjoys the one-cut solution, and there is no one-cut solution both critical curve. So presumably there is two-cut solution which we plan to investigate. So in our situation, we have, we should, in principle, we should reproduce two leads. When we have large mass, we should reduce to gravity in this graph, and small m squared we should reduce to equals results derived earlier for the d minus 2 method. And indeed, it had been shown that in the vicinity of the origin, at this region, we indeed have correct transition to the two-dimensional gravity supplemented with d minus 2 method. Let me say a bit more about the limiting procedures. So first of all, let us consider the limit to two-dimensional gravity, m tends to infinity. As usual, the heavy fermions should decouple, and we should get the pure gravity as well. It turns out to get the proper limit, we should impose the following scaling. So m squared assume beta is just cosmological constant, and let us denote b cosmological constant. And we arrived quite simple but pleasurable formula for renormalization of a cosmological constant by the heavy fermions. In the limit of pure gravity, the correct value of effective critical cosmological constant has been. In another limit, we consider the two-dimensional gravity coupled. We should derive the two-dimensional gravity to d minus 2 meter. M tends to infinity. We just use the relation between partition function of d minus 2 theory as a derivative of our partition function with respect to mass squared. And this is just the evaluation of the particular observable in our theory. And indeed, there is some collision, the collision of the critical point in the observable and the conventional Gaussian spectral density. We get the correct critical value of cosmological constant, and also critical indices in this limit are reproduced as well. The natural question, are there some special values of mass when we have new critical phenomena, apart from two asymptotes? There are several points which are under investigation. What does that mean? And also there is some more simple argument which claims that there are some non-trivial values of masses which are important. Let us use the Kirsten-McCoy spectral density, and the corresponding resolvent is just a derivative of partition function with respect to mass. And in this case, however, no planarity condition is imposed, but this derivative, due to the square root, provides some criticality at finite mass squared. So we have a new susceptibility which can be called mass susceptibility. Since it is nothing but our model is just the fermions interacting with two-dimensional gravity, then these susceptibilities are just the fermionic correlators in this case, and actually they also measure the mean number of trees in our two-dimensional surface. Another point which is under investigation now is that in the interpretation role of eigenvalue instantons. Since our potential has two extrema, then we have a very clean place for the eigenvalue instanton, and presumably these instantons should be related to the instantons which I have discussed in the first part of my paper, of my talk. So in this case, it can be shown that dependence of the eigenvalue action on the m squared is quite non-trivial and elliptic function. So this is so let me emphasize once again that the instantons in the random ergo graphs, eigenvalue instanton in random ergo graph, are nothing but clusters. So there is one-to-one correspondence between clusterization and the number iteration phenomena and the importance of eigenvalue instantons. As usual, if we would turn to kind of brain picture, it's known that instant tones can be interpreted as the so-called ZZ brains or D0 brains, but it is beyond the scope of my talk. I have 10 minutes more, and let me turn to the another point. It's really model is the same, actually the same. So we consider the massive spinless fermions on the random irregular graphs, but now the random irregular graph play a very different role. So so instead of discretization, a kind of world sheet of the string, or discretization, or formal discretization of two-dimensional surface is just the representation of the Hilbert space of interactive many-body system. So how the mapping looks like? It goes as follows. So the nodes are identified as the states in the Hilbert space. The links are identified as resonances between states. And this idea was invented a long time ago. Originally, it was suggested that dotted tree is relevant, but it turns out that it's wrong. However, later it was shown that a random irregular graph is a very good toy model for this type of problems. And now random irregular graph is very popular in the for the many-body localization. Let me say a few words about the many-body localization. It is the phase without the thermalization. So we have interaction provides the thermalization. There are hidden conservation laws in the physical space. There are there's not exact. Usually, the integrability prevents the thermalization because of conservation law. Here we have this stuff. And then it was conjecture by two group of people that when we consider many-body localization in the physical space, it corresponds to one body localization in the Hilbert space. So this is exactly the problem I have discussed. This model, they considered the spinless fermions. Fermions on a random irregular graph, the same problem. However, there is one new ingredient, the masses, and that's all. So this is the only difference with the model I have discussed before. But it turns out that this point provides you quite a non-trivial result, and it has proved exactly that there is Anderson phase transition in this model. How it could, how this phase transition could be derived? Let me remind the well-known facts that there are several tools to recognize the localization. You would consider the spectral correlator or spectral form factor. These are old tools, and also there is another old tool, so-called level spacing distribution. We could distinguish between the ergodic and localized space, looking at the level spacing distribution in the spectrum. More recent, there are two additional tools. so-called R statistics and inverse participation ratio with some parameter Q. And it turns out that this object works better for the diagnosis of localization transition. Let's back to the first part of my talk. I have shown that we have two parts in our spectrum above the phase transition. So let us assume that we are in the clusterized phase. We have two parts of the spectrum. This is just the remnant of the Wigner semicircle instead of Wigner semicircle. And this part corresponds to the clusters I have mentioned, or eigenvalue instantons. And let us investigate the ergodicity of spectral level distribution in both parts. A bit surprisingly, it turns out that here we have the conventional ergodicity, part of the spectrum. But when we consider the part, the second band populated by eigenvalue instantons or clusters, in other words, it turns out that the distribution is Poissonian. It means that the part of the spectrum corresponding to clusters correspond to localized modes. So we see that in a random regular graph perturbed by three sides, there is mobility H, which separate the ergodic and localized modes. Let us turn to another model. So once again, consider the fermion masses are random, but let us assume that no chemical potentials for cycles, just random masses. The same model, random ensemble of random regular graph, fermions with random masses, but there are some part of massless modes. Let us investigate what is impact of this massless modes on the localization properties. In what follows, this is just Hamiltonian written in terms of the same Hamiltonian written in terms of creation and annihilation of operators of fermions. And we used the R statistics and inverse participation ratio. Why it's interesting to investigate the situation in many body systems, there are closely protected modes. And it was known that these zero modes strongly influence the localization and ergodicity, and for instance, in integer quantum Hall effect, the topologically protected zero modes is responsible for complexity. And in our work, we just make this zero mode sector in the physical space, but the sector without disorder in the random regular graph. And the number of these numbers is random. And very surprisingly, it turned out that information at arbitrary disorder, there is mobility H. So of new phenomena that in this random regular graph, partially disordered, there is conductivity in this center of the spectrum. How this can be described? As I have already mentioned, there is mobility H in the spectrum at any disorder, and the tails of the spectrum are localized, while we have delocalized part inside of the spectrum. Moreover, the delocalized part of the spectrum is quite non-trivial. It can be identified as a non-ergodic and fractal situation. So let's say, side remark. It's not our problem has some similarities of investigation of Dirac operator in QCD. And in that case, instead of averaging over geometry, that is random geometry, in that case, there is integration over the instanton modular space, and also matrix model can be derived and all the stuff. And it turns out that there is the point when we have exactly similar phenomena, the emergence of mobility H, and it happens exactly at the point of black hole formation in holography. And actually, the analogy of problems of mass fermions on two-dimensional gravity and the QCD stuff developed some investigation. But don't to the last slides. Let me point just a few open questions. There are a lot of open questions. Our new matrix model should be investigated from different viewpoints. And the most immediate question concerns the investigation of multi-solution in this new matrix model generalization to Dirac fermion and Dirac fermions, and consider the random fermion mass. So the case of random fermions seems very relevant for many problems. And also, since get matrix model fermions, we should evaluate the fermionic correlators in terms of topological correlators on the modular space, and a kind of Liouville theory interpretation is actually required. And also, as I have mentioned, in the spectrum of such models, when we consider fermions interacting with random regular graphs, there are different parts of the spectrum could be different statistics. And here, it's highly interesting to investigate the spectral statistics at arbitrary value of cosmological constant, see here, and mass. It's an open question. So let me turn to conclusion. We find a new matrix model which interpolate between pure two-dimensional gravity at very large value of fermion mass and gravity coupled to d-2 meter at zero masses of fermions. It is shown that due to back reaction of matrix geometry, the geometry breaks down to the trees, and the number of corresponding trees depends on the fermion mass. So the mass plays an interesting role. It counts the number of trees in the graph. And I have also shown that generically random graph with perturbation provides the localization phenomenon in the spectrum, and it is interesting and should be relevant to the investigation of aspects of many body localized phase. And my final slide. First, I would like to say happy birthday to Mike. We met with him for the first time in Aspen in 1993. Some intersection of our scientific activities. At that time, we investigated with Nikita Nekrasov two-dimensional Young-Mills theory, and Mike derived very interesting results in two-dimensional Young-Mills theory as well. So there were some intersection of scientific interest. And a small gift, if you wish, So very recently we have a paper with such on another very different set, but now Mike has made different interests. It was attempt to somehow to explain quantity with so-called 7 plus minus 2 law. And it is the first attempt. And the paper has been published on April 1st. So you should decide yourself whether it is meaningful or not. And to conclude, it seems that Mike saturates the upper bounds in this Miller law. 7 plus minus 2 law means that the person could simultaneously have in mind not more than 7 plus minus 2 different items. And it seems that Mike saturates the upper bounds in this law. Thanks.
Thanks, Sasha, for the nice talk. So we have time for some questions. Okay, Sasha, you gave several nice interpretations of your matrix model. I think that there is another one, which is not as a sum over trees, but a sum over dilute loops on the random lattice. And this is the ON model with n equal to -2. So you have two parameters in this model. You have the parameter for the vacancies and also a parameter which governs the length of the loops. And you have it interpolates between c equal to -2 and c equal to 0. So it would be interesting to just rephrase the analysis about the multi-cut solutions in terms of this geometrical model with this neat interpretation.
Yes, so I completely agree. So we have thought that there should be a kind of we are not sure that it's exactly auto model for random loops, but it should be related to a kind of its modification. And for sure, it will be highly interesting to map and relate these two models, the one we have considered and the model of loops. Yeah, I agree.
It is exactly the loop model. There is no modification.
Yeah, I agree. We have it. It should have precisely the same critical behavior.
Not even at finite coupling. It should be the same.
But at finite coupling, I'm not sure because there are different kinds of trees.
No. You don't.
Those are loops. Those are loops. But what do you mean for finite couplings?
You can.
It's not the same model.
It is. They are related by the field transformation.
I know what you mean, but I thought
the potential could be different.
Yes, it's the same. Yes.
That I'm not sure about. So you can derive this potential which we have.
Actually, we computed the O-2 model with Matthias. It's just using this trick, writing it as a one matrix model with square root.
No, I understand that it can be written, but for example, Potts model, is it the same?
Oh no, it's not possible.
We know.
It's difficult.
But actually, then the question to you about your model, if it should be similar to ours, do you have finite? Do you have a phase transition from these trees, which is C equals 0, many trees,
Yes.
to almost spanning trees
Yes.
for finite coupling, or it simply approaches as interpolating.
Yes, you change the parameter that governs the length of the loops, and then you have transition from small loops, which is pure gravity, to loops that fill the space more or less, and you have a.
So it's a finite. There is a finite.
It's a finite
point for its transition. Okay.
So maybe we have to we can discuss later. Let's thank Sasha again for this nice talk. Maybe you want.
Yeah, we'll ask something.
Oh, sorry. We have 2 minutes. We have 2 minutes.
Sasha, any connections of your random graphs analysis to your work on connectome, no brain activity?
Oh, not yet. So actually, this is another story. Connectome is very interesting, and actually,
Not connected.
not today. Actually, I thought which type of top would be more relevant for this event, because Mike works on connectome as well. But I decided to discuss this issue. Yeah.